Hi, welcome to week 11 CSM. I'm Akshay, if you don't know that already. Yeah, so today is going to be some more scheme, scoping, and interpreters. So this is going to be sort of leading into your scheme project, and you're just gonna, we're kind of going to build on like what we did last week with scheme, except we're going to talk more about how the language works. So as a recap, call expressions in scheme follow this thing called prefix notation, where the first thing you have is your operator, and then you have these operands. And how it works is you basically evaluate the operator, then you evaluate each of the operands, then you apply operator onto the operands, same as Python. So in Python you had this like function f, that would be the operator. You had these two operands, x and y. So it's the same thing. This is just a little different from like infix notation where you have the operator in the middle. So like some convenient things you might have seen in Python where like, oh, you could do like 5 plus 5, where this plus operator is actually like right here. So yeah, that's kind of the difference. But everything in scheme is sort of this prefix notation. So yeah, keep that in mind. Special forms are something that look like these call expressions, except they're not. So what's different about these is that they implement these like different scheme language features, which means that they can't follow the same like evaluation rules. Namely, like you won't be evaluating all of your operands. So an example of this is just the scheme if statement, where let's say we have some if, and our condition is just if 2 equals 2, it does. And then if it does, we return 1. Otherwise, we print 5. So if this was just like a regular call expression, right? Then what we would do is we would evaluate each of these. But we don't actually want to do that, because in the if statement, we only want the else case to happen if the condition is false. So we never want this print 5 to get evaluated, because 2 is actually equal to 2, so we just want to evaluate to 1. So that's short-circuiting. That's the best example of like these special forms at work. And there's actually a lot of these special forms. So you have define, if, cond, and so on. We're not going to talk about them in detail, but just note that they're different from like the built-in procedures. So like some of the built-in procedures are like maybe the plus operator, or actually like the list operator is built in. Reason why is because it actually does evaluate all of its operands. That's a quick test to see. Okay, let me just erase this. I was doing it earlier. Okay, so I'm gonna make you guys pause and just do the first part and then check back in with me. Okay, let's begin. So the first one is just a simple if statement. As a reminder, the only false value in scheme is hashtag f. So this is our only false value. So in this case, 1 is true, so we'll just do the true condition. So the first one is a true condition, the second one is the false condition, and so we just do the true one, so we evaluate to 1. Okay, next one. This is 0 in here, so in Python this would actually do something different, but 0 is true in scheme, so this is going to try to evaluate this like /10. And just like in Python, we throw a division error because there's nothing like more sensible to do when you're dividing by 0. So this is just going to be an error. Okay, what happens here? Does this one error? Well, we have an AND statement, and we know that AND statements do some short circuiting. So just like in Python, the way AND statements short circuit is they return the first false value. Or if there are no false values, they return the last true value. So, or the last true. Okay, so in this case, there is a false value. So that's what's going to happen here. So the first value is 1. That's true, so we're all good. But then we see this false value and we realize, oh, this AND doesn't need to operate the remaining ones anymore. So this is just going to return hashtag f. So this is another example of this like special form short-circuiting at work where you don't actually evaluate the /10, and you're not going to get this error. Okay, AND of 1, 2, 3. This is an example of all of these being true. If they're all true, you just return the last one. Okay, or. So OR is pretty similar, except OR will return the first true value. So remember, OR is just looking, oh, is there a true value in whatever you've passed to me? So it doesn't need to keep looking once it's found one. So first, this thing is false, so we don't care. False again. 0 is true, so OR will just return this 0. Okay. If you didn't pause to do the rest of them, I recommend you pause to do this specific question. It's pretty good. Yeah, so the default behavior of AND and OR, you can sort of reason about, where AND is supposed to be, oh, it's looking for, is everything you gave me true, right? And in this case, you gave it no arguments. So when you give it nothing, everything you gave it is true. So the default behavior is just to return true. For OR, you're checking, oh, does there exist a true value in all of the values you gave me? Well, we gave it nothing, so there doesn't. So this will return false. And the output wouldn't actually change based on like the default. No, actually, never mind. Take that back. Yeah, so you're going to do AND of true and false. So it just skips over this true and then looks on the next value, and then it'll return the false because that's the last value. Okay, so we're defining A to be 4. This just returns the symbol. It's just a scheme thing. That's A. And now we're doing these different lambda expressions. So lambda expressions in scheme are pretty much the same as lambda expressions in Python. They're just anonymous functions, so functions without a name. So as opposed to define, where you would give a name here, these are just the two parameters for lambda. So these are the two arguments it takes, and then the ones you're passing in are 1 and 2. So this x gets bound to 1, y gets bound to 2, and we do plus, so a plus x plus y, and that's equal to a plus 1 plus 2. Now what's this a? This a actually exists in our global frame. So don't forget your kind of like scoping rules from Python. Those are actually pretty similar in scheme, where you look in the frame that you're currently in, but then if you don't find your variable, you look in the parent frame of that. If you don't find your variable there, you look in the parent frame of that, and so on until you get to the global frame. So in this case, we found a in our global frame. So we'll just say this is 4 plus 1 plus 2. So that's 7. Okay. The next one is another lambda function. This one's a little weird because you have this like sort of odd expression yxz inside the lambda. But let's try to figure out what it could be. So the arguments we're passing in is x is 2, y is this division symbol, and then z is 2. So what this means is that the inner expression is going to be evaluate divide, then evaluate 2 and 2, and then apply divide onto 2 and 2. So what it turns out to be is just another call expression where y is your function. And this is a pretty important concept in Scheme 2, where everything that's a list is either a call expression or a special form. So y is always going to be treated as this like operator. So this slash is going to be our operator. We're going to do 2 divided by 2, and that's just going to give us 1. Nice. The last one is also a little odd. You have this variable, this function x, and you're applying x onto itself. So yeah, this is a little weird to think about. Let's see what it does. So x is bound to this lambda function, and what we're doing is applying this lambda onto itself. So that means y, the parameter of the lambda, is also bound to the lambda function. However, if you'll notice, this lambda function always returns 4. So it doesn't care about what y is, it always returns 4. So once again, this is like calling this lambda. I'm just going to define a function for clarity's sake. So let's say we had a function f, which took in a parameter y and then returned 4. So here what we're doing is calling f onto some arbitrary argument, x. But it doesn't care, it just returns 4. So this whole thing would just evaluate to 4. Okay, let's do part 2. Once again, pause and come back. Okay, so we're defining boom1 to be this weird expression. This expression is a divide by 0 expression, and we know we don't like those in Scheme. So this actually errors. And it's probably important to remember this distinction because even though define is a special form, it's not like a hard and set rule that special forms don't have to evaluate all of their operands. It's just that they don't evaluate some of them. So for example, boom1 is not actually evaluated, right? Because if you try to evaluate boom1, you'd get an error because it doesn't actually exist. But define evaluates whatever value you're assigning to. For example, yeah, this is a good example. It would evaluate this like /10. So then you'd actually get an error, as opposed to just like skipping and delaying evaluation. Speaking of delaying evaluation, you have boom2 being assigned to a lambda. And this is actually perfectly fine. As long as your lambda has like a valid definition, you can assign it. Because in Scheme, just like in Python, you're not going to evaluate the body of a function until you call it. So you're never going to get this error until you call this function, which you actually do right here. So when you call this function, you'd go through this body, and then you'd get the error. How are these two different? Well, one is just defining like it to be an undefined value, and then the other is defining it to be a lambda. Okay, part B. There's something odd about this like expression here, right? Because we have boom2 and it's assigned to a lambda. This is not typically how we write functions in Python either, right? If we want boom2 to be a function, we can just use our typical like function notation. We don't need to introduce like a special lambda in here, call it anonymous, but then assign it to a name anyway. That kind of ruins the point. So we can just use our regular define notation to rewrite boom2 without the lambda operator. So the name of the function is boom2. Well, does the lambda take any parameters? No, it doesn't. So we can just close this. And then what's in the body? That's just /10. Okay, let's do number 3. Look away. Let me just delete these answers. Okay, so define C2. Once again, that's just C. Eval, quote C. What does eval do? Well, just like any other call expression, eval is first going to evaluate its operator. So this would evaluate to C. But then eval actually evaluates whatever value is passed into it. So eval is basically going to be doing like 2 evals. So evaluated this quote C into just the letter C. And then this is like putting this into the scheme interpreter, right? Scheme interpreter just evaluates whatever you give it. Well, C would evaluate to whatever the value of C is, which is 2. So this is just 2. And this is actually a pretty subtle but important point. Scheme can delay evaluation, and you can have sort of these layers of different evaluations. So if I had something like quote C, the first time, that would just evaluate to quote C. But then I could evaluate this quote C, and then that would evaluate to C. And then that C would evaluate to 2, and so on, right? So that's kind of like the beauty of the scheme language, that the fact that you can delay evaluation in this manner, and that you can write like these symbols that don't necessarily need to be evaluated now. Okay, so next we have this quote form. Quote just takes everything that's given to it and literally returns it. So this is just going to return cons 1 nil. Now what happens when we call eval on this? So this is first going to get evaluated. So we're going to evaluate to cons 1 nil as we did earlier. And then we're going to evaluate it again. So I'm going to put this in the scheme interpreter just for more clarity. Cons just creates a list with both of the elements. In this case, there's just that one element. So this will be a list with 1. Okay, this last one. This one is super interesting. It kind of shows you how the scheme language works. So this one is creating a list. Okay, creating a list with if even question mark C 1 2. And the reason why I got rid of the quotes is because list is evaluating each of its operands. So this quote if just evaluates to if. And notice this looks very familiar. This looks like just as if we just typed this entire if expression into Scheme, right? And that's not a coincidence. In Scheme, you can write code. Everything is written using lists, and everything is represented using lists. So if you just make a list of all of these things, that's equivalent to just writing like this if statement itself. So the last thing we're going to do is actually call eval on that, since we need another layer of evaluation. So calling eval on this thing, we're not calling on eval on that, we're calling eval on this, which evaluates this. Sorry, I'm saying this too much, which evaluates this, and then evaluates it again. So evaluating it again is like putting it into the scheme interpreter, and we say, is C even? C is 2, so C is even, so we just return 1. Okay, I'm going to pause here, make sure the recording's going okay, and come back. Okay, we are back. So let's talk about scoping. So there's two kinds of main scoping. Mostly you encounter dynamic scoping. Lexical scoping mostly, which is how it's done in Python. And what lexical scoping means is that the parent, let me get lexical here, of a function is the frame in which it was defined. And what that basically means is that if I define some function f or foo like right here in the global frame, then its parent is just the global frame. However, I define this lambda inside this foo. So let's say this foo is called and we open a new frame f1. The parent of this lambda would then be f1. So that's lexical scoping. We're going to get into the example here. But the other kind is dynamic scoping. So the way dynamic scoping works is that it makes it such that the parent of a frame, of a function, is the frame in which it was called. So this is actually sort of like a misconception that happens like early on, and they try to trick you in like the environment diagrams and stuff, where they define a variable in some frame, and then they call a function inside that frame. But that variable name is not actually, sorry, I misspoke a little bit. But the gist is that the parent of a function is the frame in which it was called. Oh, okay, I just got my train of thought back, but I will try not to confuse you. Nice. Yeah. So let's just kind of try the example. So what would this print using lexical scoping? So this is just like what we typically do in Python. So I'm going to bring back the environment diagrams. A is 2. Foo is some function whose parent is global. And then we say this variable bar is the result of calling foo. So then we open a frame for foo. And we say A is 10. I'm going to try to make this less formal of an environment diagram because they're getting kind of annoying. And the return value is this like lambda, right? And that's actually what bar points to. And this lambda's parent, that's kind of the important part here, is foo's frame, right? And foo is in, let's call it f1. So lambda's parent is f1. Okay. Now when we call this bar of 10, we're calling this lambda with x equals 10, right? So we have this lambda where x is 10, and it returns x plus a. Now we know x is just in our frame. What's a? Well, a is actually in our parent frame, f1. So a is right here. So we're going to use 10 plus 10 equals 20. So that's what we're used to doing. Now let's try dynamic scoping. So in the case of dynamic scoping, you're calling this function bar of 10 inside the global frame, right? So we're not going to give lambda a function right here, a parent right here. But this bar over here, it's getting called in the global frame. So the parent of this lambda is actually the global frame, which means that now when we go to look up this variable a, we actually look in the parent of this lambda function, which leads us to this a right here, which is actually 2. So this can be useful sometimes too. I don't have a concrete use case right now. I think lexical scoping is more common, but that would just print 12. So our answers were 20 and 12 respectively. Okay, how would you modify an environment diagram to represent dynamic scoping? We kind of just did that. The gist is that you only label parents of functions when you call them. So like label this p equals g, but don't label anything right here. All right, this next part I'm actually going to skip over because I think there's some pretty good videos about it. I saw them on the 61A Piazza, so I encourage you to check those out instead. But yeah, I'm going to zoom out here in case you want to do it. I'll probably just send over the PDF of the worksheet as well. All right. So now we're just going to get to the coding questions. So there's 3 of these. Yeah, let's start with the first one. So this is just to get you more familiar with scheme, recursion and scheme, and so on. And yeah, so the first one is prefix. So is prefix is taking in a list, p, another list, and then checking if p is a prefix of list. So what does a prefix mean? Well, prefix is anything that, well, they say it right here. If list starts with all the elements in p, then p is a prefix of list. So like with words, for example, if you had like A, B, C, E, F, G, then ABC would be a prefix of this. ABCE would be a prefix of this, and so on. So with lists, it's kind of the same thing, where if you have like a list 1, 2, and then you have another list 1, 2, 3, 4, 1, 2 is a prefix of that. Let's look at like the examples that they give us. So for an empty list, they're just returning true. An empty list is a prefix of an empty list. Is an empty list a prefix of like a non-empty list? So is this guy a prefix of 1, 2? We typically say that's true too, because there's just nothing in this like list. Yeah, so like it's kind of like asking, is like the empty string a prefix of A, B, C, D? Which we typically say it is, as a nice base case. Okay, and now we have the actual example. Is 1 a prefix of 1, 2? It is, because 1 is the first element. Is 2 a prefix of 1, 2? It's not, because 2 is not the first element. So we don't care if it's contained, we care if it's actually the prefix. Okay, so this is going to be a recursive question, like pretty much all of the ones that we do. So we're going to have to try to come up with some base cases. And for that, I'm going to actually use these doc tests. Sorry. Yeah, so the first doc test here is just 2 empty lists. So this might be a case. This doesn't really give me too much insight. Let's look at the second doc test here. So in the second doc test, you had an empty list as your prefix, and your list is actually like non-empty, right? And in this case, we want to return true. Reason being because an empty prefix is always valid. So the first thing we can check is, oh, is our prefix empty? Another way of writing that is if it's null. So if it's null, then we return true. Okay, what other conditions do we have? Well, consider the like opposite case, where your prefix is actually non-empty, and then your list is empty. Well, this wouldn't work, right? Because 1, 2 is obviously not a prefix of this empty list. And plus, like, we can't be doing any comparisons between this guy and the empty list, because that would give us errors. So we want to deal with this case immediately. So we're going to say if list is null, and notice we've already checked if prefix is null. So we already return true in the case that it's valid. Then we return false. Okay, now what's our sort of last case here? How do we actually check if something is a prefix? So let me present you an example. Let's say we have 1, 2, and then we have 1, 2, 3, 4. Well, the way we can check that is we can say, okay, do their first elements match? 1 and 1, they do. Okay, do the rest of their elements match? And another way of saying do the rest of their elements is match is like calling prefix on this list with 2 and this list with 2, 3, and 4. Because we already checked the first one, so we only need to check the rest. And then so on, you'd kind of call prefix with this empty list, and 3, 4, and what do you know, you're already at your base case. So let's see what we checked here. Otherwise, we're saying if the first elements are equal, so equal car of prefix, we already know that they're not null, so that's fine, and car of list. Then we want to call prefix on the rest of this. So is prefix on the cutter of both of these. So that's cutter of P and cutter of list. And then otherwise we just want to return false because they didn't match. And actually another way you could write this if expression is just by using an and statement. Because notice we want to check, oh, do these guys match? And is the rest of it a prefix? So instead of writing if, I could literally just substitute this with and then I don't need this like false condition, because and is going to return false if one of its things is false. And so if you're not equal, then it's going to return false, or if there's no prefix later on, it's going to return false. Yeah, that's is prefix. Let's do the other two. Okay, so apply multiple. This might be something you've done before in Python. It takes a function and it applies it to some value, a total of n times. So if I had, say, like this multiplication function, it's going to apply it to 3 2 times. So that is squaring function actually. Or sorry, it takes f and then, oh, it's going to apply it to 2 3 times. My bad. So that would be 2, 4, 16, and I guess 16 squared is 256. So that applied this function 3 times. So let's think about how we could do this. Well, let's first think about how we're going to like structure it to reach our base case. So you have this like function that's being applied n times. Well, the recursion here is sort of that you could pass in a value like after applying the function once, and then decrement the number of times you wanted to call it. So once again, like, oh, if you wanted to call the function 4 times, or 3 times in this case, well, you just pass in the 4 and say, okay, I only need to call it 2 more times. And so on, you pass in the 16, and you only need to call it 1 more time. And then you pass in the 256, and then you're done. So when your number of times is 0, then you're done. You just return the value. So if n equals n0, we just return x. Otherwise, we want to do something else. Namely, we want to call this like apply multiple thing, right? But we want to modify our arguments like we did kind of up here in my example. Well, I want to call apply multiple, so let's write that. Our function remains the same. What happens to our n? Well, we're going to be one step closer to getting our solution, so we're going to decrement n by 1. And then lastly, our x is going to be actually like one step closer to the correct one, right? So we're going to be applying this function f onto x. So in this case, we like squared 2, right? Or squared 4, and so on. So our x is going to be like f. Yeah, that should work. I encourage you to kind of go through a test case and make sure like I didn't mess up an edge case here. But yeah, I think it looks good. Let's go to the next one. Okay, so this last one has 2 parts, this sort of mini function and then this bigger one. Once again, I encourage you to pause and try it, and then we'll go over it. Okay, I hope you found a solution. Let's talk about it. So the first part is just implementing a max function, so it's just going to take x and y, and then it's going to return the max between x and y. Well, we can just do this with a simple if statement. We'll say, oh, if x is greater than y, then we just want to return x because it's the bigger one. Otherwise, we want to return y. I hope that's clear. Okay, this other max depth function, what it does is it actually returns the maximum depth of a nested list within this list. So, in the example of like just this like list that doesn't have anything nested in it, that's going to return 0. However, you have this other list where you have this one list nested inside it and then another one. So this guy is actually going to return 2 because there's two nested lists at the at best. And then the last one is like a whole bunch of nested lists, smaller and smaller, and that's just going to return 4. So they've already kind of defined a helper for us. Let's see what parameters they have. So the helper is going to take the list, which is the same as like before, but it's also going to take this value cur. Well, what could cur be? Think about what you need to keep track of. The thing that you're trying to output in this function is the depth. So maybe cur could be like your current depth. So let's go with that idea. And maybe we'll start by just calling this function. So in your like whenever you define these helper functions, typically in your like main function you call and return the result of this helper function, right? So on the outside we're just going to be calling this helper. Well, we just want to call it on our regular list. And what's our current depth? Well, we look at our like first like base case. The depth was 0, so we just return 0. Okay. So let's think about some like base cases here. So let's say I gave you an empty list. Could you tell me what the depth is? Yeah, you would say it's 0, right? In this case, what if this empty list was like inside this other list, right? Then the depth would actually be 1. So we want to, that's why instead of returning 0, we want to be returning actually this like cur parameter. We're just going to keep track of what our depth is. So if list is null, we'll return cur. Otherwise, they're checking another condition in here. And the condition they're actually checking is that we actually have like, okay, let me break it down with an example first, actually. So let's say I have some list, 1, 2, and 3, right? Well, this first part of this is a nested list. So all we could do is just kind of call our helper. We could say, okay, what's the depth of this list? Well, it's 0 plus the depth of our parent list, which is kind of cur. So this would actually be 1. And then we check the depth of the next item in here. And we say, okay, what's the depth of this? Well, this doesn't have a depth because it's just an element. So this is just going to return 0. And then lastly, maybe I added another one in here. 2, 3, 4. Well, for this guy, you'd call depth on this whole thing. That would return 1. And then you'd add it to whatever depth you're actually in. So since this is a nested list, it already has a depth 1. So this would be 2 then, for the deepest one. So what I was trying to get at was that first, like, the things in the list don't actually have to be a list in here, right? So like this 3 is, for example, just gonna like kind of get skipped over. We're not gonna change our current depth because we reached this element 3 because we haven't found something deeper. So in here, we're just gonna check if the list is actually, if the first element is actually a list. So I'm going to check if the car of list is actually a list. And the way we do that is using the pair operator. I believe there's actually a list question mark operator too, but I'm not too sure. So now we're going to be taking a max over something. So what are we taking the max of? Well, we're taking the max over like the depth of this first guy. So this guy. And then like any depth that we find later on in here, right? So the first, the depth of the first guy is just calling our helper function on car of list, And our cur now gets incremented, right? Because we're going one layer deeper. The other thing that we're calling it on is sort of this like rest of the list. In this case, our cur actually doesn't change because we're not going inside a list. We're just iterating through the remaining parts of this list. So now we're just going to call helper on the cutter of this list. So that would be all the elements except for this list 1, 2. And then we're going to keep cur the same. Okay, and what's our last case? Well, our last case is when we have like this 3. Well, we just want to skip over the 3. We don't really care. So we'll only call helper on the cutter of the list, because there's no like deeper list to go into. Hence, we don't need this like top case, and we don't need to maximize between anything. Okay. Yeah, I hope that makes sense. I believe my explanation got a little convoluted, but as I read the code, I think it got clearer. So, yeah. Hope you guys found this worthwhile. I will see you next week.